Hi, my name is Emily Ortega. Today we will be going over mass spec, IR, proton NMR, and carbon NMR to identify an unknown compound. Here we have our mass spectra, and I'm just going to write our formula down here that was given to us, which is C6, H12, O5, and the molecular weight is 164. And as you can see right here, that is our M plus peak. And then our base peak is here at 60. But that actually doesn't really correspond to any of the fragments. And let's see our degrees of unsaturation. Two times the number of carbons plus 2 minus the number of hydrogens over 2 equals 1. So we have 1 degree of unsaturation, which means we'll either have 1 ring or 1 double bond. And the only peak that I see is kind of high here that could correspond with a fragment is here at 43. And 43 can either be a CH3 CH2 fragment or a CH3 CO fragment. And that is all for mass spectra. Here is our IR spectra, and as you can see, I've already split up the zones so it's easier for us to go through. So as we go into zone 1, this sort of tongue stretch here with little peaks at 3,339 and 3,252 are actually significant of alcohols and phenols. So in zone 1, we have alcohols and phenols. And then in zone 2, we have this small peak right here, which is actually significant of either a carboxylic acid or an alkane. And then as we can see in zones 3 and 4, we don't have anything. And then in zone 5, we have this peak here at 1,464, which is actually reminiscent of an aromatics, which matches up with our degree of unsaturation that said we either have 1 ring or double bond. So that actually matches up with our DOU. Okay, and then in our fingerprint region here, we have these really 2 strong peaks at 1,000 and 782, and then 1,000. That peak really represents esters, ethers, alcohols, and any carboxylic acids. And then at 782, it doesn't actually fit with our formula because that represents primary and secondary amines and alkyl chlorides. Okay, so we have ethers, alkyls for our fingerprint region. And that is all for IR. Here we have our proton NMR, and as you can see, all the peaks are already integrated, and I actually have a zoomed up version of this section right here, which looks like this. And right now I'm going to draw a proposed structure based on what our mass spectra and our IR spectra told us, which here is just a reminder of what our formula is. We know from IR it's going to be a ring, as well as from our DOU that it's going to be a ring. We know that we have alcohols, and this fragment from the mass spectra is what makes more sense, and then that there's also going to be an ether. So I will be right back with the proposed structure. Hi, so now I'm back and I have our proposed structure drawn out. And now we're going to look at both the zoomed in version and the whole HNMR to see if we can match up these hydrogens. So actually, before I match up any of the hydrogens, we're going to take a look at that we have some exchanges here. So we have a 1H exchange that I'm just going to X out, and a 2H exchange that I'm just going to X out because that's just due to how many oxygens there are because they're so electronegative. They actually have little readings that pop up on HNMR. And in the zoomed in version, we're going to do that as well. Just mark out this 2H exchange, which was just the same one that I had marked out right here. The first hydrogen environment that we're going to match up is going to be that CH3 because it's the easiest to identify, and it's with this 3H right here. So we're just going to circle these hydrogens, and they go to this peak. Right there. Then this hydrogen matches up with this 1H peak right here next to the 1H exchanges, which the 1H exchanges, the hydrogens that correspond with that are these three alcohols. Those are actually responsible for that 1H exchange reading. I'm going to have to take a closer look at this zoom in version that includes that 3H peak that was representative of the CH3, and these 5H's here, which as you can see is split up into a 1H reading, a 3H reading, and another 1H reading. So one of those 1H readings, which is representative of this one right here, is going to be the one that is furthest downfield, which we're just going to overlap this right here, That 1H reading is representative of that hydrogen. And then as we keep going, this hydrogen right here is going to be the reading for this hydrogen. Just we can go and show. And then these hydrogens all being connected to a carbon that's also connected to a alcohol actually are represented in this 3H reading. So let's circle these three and then just connect them down. And they all match up for these three in those readings, and then the other two match up on the zoomed out version, with this 1H being representative of that one and the CH3 being represented there. So that shows that our proposed structure is correct, and that is all for HNMR. Carbon NMR, and as you can see, I've already labeled each peak. Now there's 3 peaks right here on top of each other, so I just wrote the number corresponding to the numbered peak. So we have 1, 2, 3, 4, 5, and 6, which match up with our number of carbons in our formula, which is C612O5. So now we are going to match up the carbons with their corresponding peak. So let's see. We know that CH3 is going to be the least downfield, so CH3 is actually going to be matched with 1. So 1's right there. Now let's see. Actually, sorry. Yeah, with 1. Okay. Second least de-shielded carbon is going to be the CH2 that we have right here. So that's going to be number 2. And then what these 3 are, since they're all very similar, are going to be the carbons corresponding to the alcohols. So let's just label those right now. This one is 3. This one is 4. And this carbon is 5, which leaves our 6th and most de-shielded carbon to be right here. So as you can see, we have labeled all of our carbons correctly. And now let's draw arrows. This one goes here. That one goes there. This is actually not a reading. It goes here. And then we have 3, which is right there. 4, right there. And then 5. Okay. So that works. And that is our carbon NMR. Hello, I'm Amelie Ortega. I hope you enjoyed watching this video, and I hope it will help you on your future endeavors of analyzing spectra.